Namaskar. Today I will discuss the principle of least action. Action in mechanics. Now statement. In mechanics, the times integral of the toy, the kinetic energy, is called the action. Thus, A is equal to integral from t0 to t1 to t dt. It's called the action, that is A is equal to integral from t0 to t1 summation of pj qj dot dt. It's called action in mechanics. Principle of least action. There is another variational principle associated with the Hamiltonian formulations and is known as the principle of least action. It involves a new type of variations which we call the del variation. In del variation, the corresponding coordinate of the endpoints remains fixed while the time is allowed to vary. The varied path may terminate at different points, but still position coordinates are held fixed. Mathematically, we have delta I is equal to dou I by dou alpha d alpha, and del I is equal to di by di by d alpha into d alpha. Thus, for the family of path represented by the equation qj is equal to qj of alpha t is equal to t of alpha, we have delta del qj is equal to dqj by d alpha is equal to dou qj by dou alpha plus qj dt by d alpha. Again, del qj is equal to dou qj by dou alpha d alpha plus qj dot dt by d alpha. Delta qj is equal to delta qj plus qj dot delta t. This shows that total variation is the sum of two variations. Example on principle of least action. If f is equal to f of qj dot t, then show that delta f is equal to delta f plus del t df by dt. Solution. Consider a system of particles moving from one point to another. Let the family of position path between these 2 points be given by qj is equal to qj of t alpha. In del variation, time is not held fixed. It depends on the path. This implies that t is equal to t of alpha. Since f is equal to f of qj dot t, then we find del variation in f as del f is equal to summation of dou f by dou qj delta qj plus dou f by dou qj dot delta qj dot plus dou f by dou t delta t. However, we have delta qj is equal to del qj is equal to delta qj plus qj dot del t. Similarly, we find del qj dot is equal to delta qj dot plus qj dot delta t. Using equation 5 and 6 in equation 4, we get del f is equal to dou f by dou qj delta qj plus qj dot delta t plus dou f by dou qj dot delta qj dot plus qj double dot del t plus dou f by dou t delta t. Del f is equal to summation of dou f by dou qj delta qj plus dou f by dou qj dot delta qj dot plus dou f by dou t dt delta t plus summation of dou f by dou qj delta qj dot plus dou f by dou qj dot qj double dot plus dou f by dou t delta del t. Note here that the term delta t added because it is 0, since in delta variations time t is held fixed and consequently change in time t is 0. This can be written as del f is equal to del f plus delta t df by dt. Since f is arbitrary, we can write it as del is equal to delta plus delta t d by dt. Next theorem, for a conservative system for which the Hamiltonian H is conserved and principle of least extension state that del integral from t0 to t1 summation of pj qj dot tt is equal to 0. Consider xy coordinate system. In xy coordinate system, two curves a, b and c, d. Suppose that a at t0 at the distance 0 at the time 0 and AC suppose t0 plus delta t0 and t1 plus delta t1 del t1. Consider a conservative system for which the Hamiltonian H is conserved. Let AB be the actual path and CD be the varied path. In del variation, the end points of the two paths are not terminated at the same point. The end points A and B after del T takes the positions C and D such that position coordinate of A, C and B, D del T take the positions C and D such that the position coordinate of A, C and B, D are held fixed. Now we know the actions is given by del A is equal to integral from t0 to t1 summation of pj qj dot dt. A is equal to integral from t0 to t1 l plus l dt. A is equal to integral from t0 to t1 l dt plus l t0 to t1. A is equal to integral from t0 to t1 l dt plus h t1 minus t0 del A is equal to del l dt integral from t0 to t1 plus h del t0 to t1. Since time limits are also subject to change in del variation, therefore del can't be taken inside the integral. Let integral from t0 to t1 l dt is equal to 0. Therefore I dot is equal to l. Therefore del t is equal to delta I plus I dot del t. Thus we have delta del integration of t naught to t1 L dt is equal to delta integration of t naught to t1 L dt plus L delta t del t naught to t1 del integration of t naught to t1 L dt is equal to integration of t naught to t1 summation of dou L by dou qj delta qj plus dou L by dou qj dot delta qj dot plus dou L by dou t delta t dt plus L delta t. Since in delta variation time is held fixed, therefore del t naught to t1 is equal to 0. Therefore del integration of t naught to t1 L dt is equal to integration of t naught to t1 summation of dou L by dou qj delta qj plus dou L by dou qj dot delta qj dot dt plus L delta t naught to t1. Using Lagrange's equations of motion, we write this equation as del integration of t naught to t1 L dt is equal to integration of t naught to t1 summation of pj delta qj plus pj delta qj dot dt plus L delta t naught to t1. Since delta dqj divided by dt is equal to d by dt of delta qj, hence we have del integration of t naught to t1 L dt is equal to integration of t naught to t1 summation of pj dot delta qj plus pj d by dt of delta qj dt plus L delta t naught to t1. Delta del of integration of t naught to t1 L dt is equal to integration from t naught to t1 d by dt of summation of pj delta qj dt plus L delta t naught to t1. Since delta is equal to del plus delta I del I d by dt, hence our integral becomes del of integration of t naught to t1 L dt is equal to integration from t naught to t1 d of summation of pj del minus del t d by dt of qj dt plus L delta t naught to t1. Del integration of t naught to t1 L dt is equal to pj delta qj t naught to t1 minus pj dot del qj dot delta t naught to t1 plus L delta t naught to t1. Since in delta variation position coordinate at the end point is fixed, therefore delta qj del qj at t naught to t1 is equal to 0. Therefore summation of del of integration of t naught to t1 summation of pj qj dot dt is equal to 0. Thus the system moves in phase such that del variations of the line integral of the tau is the kinetic energy is 0. This proves the principle of least action and so on.